Good morning, everyone, and welcome to Math Mondays. Together, we're going to be exploring big ideas in math, like place value, for learners just like you. Today, we're going to further explore the concept of place value. Last week, we read the book Zero the Hero by Joan Holub. Do you remember the story? We learned all of the rules that go with zero when we talk about math operations. We learned about adding and subtracting and how zero is almost invisible when we do those two operations. Remember that when we add and subtract, the number that we start with stays the same. Then we learned about division and multiplication. We learned that zero cannot be used to divide another number. And we learned that when you multiply with zero, the product becomes zero. We also learned that in order to make numbers larger than 9, we need the number 0, and that's what we're going to talk about today. So today, as we're talking, our main focus is going to be this idea. Two-digit numbers are made up of tens and ones. That means anytime you see a number that is made up of two numbers, those numbers have different values. Our lesson looks very different today, so please make sure you have a pencil, and let's get started. Our objective today is I can identify tens and ones, and I can compose and decompose numbers. If you don't know what tens and ones are, don't worry yet. We'll get there. When we talk about composing and decomposing numbers, do you know what I mean? When we compose numbers, we put them together. For example, 2 and 3 make 5. Or 6 and 3 make 9. And when we decompose numbers, we take them apart. For example, 10 is made up of 5 and 5. Or 14 is made up of 8 and 6. So today we'll be working on identifying tens and ones, composing and decomposing numbers, and we're going to do this through a problem-solving problem. Are you ready to get started? The tools that we'll be using today are a 10 frame, red and yellow counters, and base 10 blocks. We need to think about what we already know before we get started for the day. So some things that we already know are that this is called a 10 frame. We know lots of things about the 10 frame. What can you tell me? Great. When we fill one row of the 10 frame, that makes 5, and we know that. We could count them here. 1, 2, 3, 4, 5. So when you have one row filled, whether it's the top row or the bottom row, that makes 5. When you see a completely filled 10 frame like this one here, what do we call that? You guessed it, a 10. You're right. A full 10 frame has 10 counters in it. We also know that this cube, well, it's a square right now, but this block represents 1, and that this rod represents a 10. A 10 is made up of 10 ones. We're going to talk a little bit about that today. So let's think about it. Our problem solving today says, Fidel buys 2 boxes of apples. There are 10 apples in each box. He also buys 1 bag of apples with 7 apples. How can we model how many apples Fidel bought? Can you think of some ways that we talked about modeling numbers just a second ago? I think I would choose to use a 10 frame here to model the apples that Fidel bought. What do you think you could use? Let's start with 10 frames. I put 3 here on the screen, just in case we need that many. How can we organize the apples into the 10 frames so that they're easier to count? Can you think of a way? That's right, we could put them in the 10 frames. So let's go ahead and do that now. So in order to model how many apples Fidel bought, we need to move the apples into the 10 frames. This will make it easier to count later. So as we're moving the apples into the 10 frames, have you already added how many apples Fidel bought? There, one 10 frame full of apples. Do you remember how many apples is in a full 10 frame? That's right, 10. Good job. So we'll keep moving these in order to sort them and organize them so that they're easier to count later. And when we do that, when it's all finished, this is what we get. So how many apples is on the left 10 frame? We've already talked about it. We said that was 10 ones, and we know that 10 ones is equal to 110. But now we have another full 10 frame, so that should be easy, right? One full 10 frame equals a 10. So now we have 110 on the left, 110 in the middle, and how many do we have on the right side? Can you count them? 1, 2, 3, 4, 5, 6, 7. But that's not a full 10 frame, so what do we call those? That's right, 7 ones. So we can model how many apples Fidel bought by placing them into 10 frames. Can you tell me how many apples Fidel bought in total? How many did he buy? That's right, he bought 2 10s and 7 ones worth of apples, and that equals 27. Great job. Here's another way that we can model how many apples Fidel bought. I've organized these apples into rows of 10. But you'll notice the bottom row isn't complete. Do you remember why? So when we talk about modeling this way, we are going to use base 10 blocks. And base 10 blocks look like this. So at the beginning, we talked about 1 rod equaling 110, but do you remember how many ones are in a 10? That's right, there are 10 ones in 110. So the first row of apples makes 110. That means the second row of apples, how many does it make? That's right, 110. And then the apples on the bottom, do you remember how many were in the extra 10 frame? That's right, there are 7 ones in that row. So modeling this way gives us a different way to look at the same number, 27, as 2 10s and 7 ones. Now, when we were reading about 0, we talked about the numbers 5, 50, and 500. Can you guess, how are those numbers different? How are they the same? We know that we talked about 5, but what does 5 mean? What does it mean to have 5 of anything? 5 puzzle pieces, 5 Legos, 5 flowers in your garden. If you have 5, that means you have 5 ones. And here you can see 5 modeled in a 10 frame and with base 10 blocks. We're going to need that to compare 5 to what's next, 50. How is 50 different? Yes, it has a 0, but what does that 0 do to the 5? Well, instead of being 5 ones, now we're dealing with a different place value. And when we model 50, there are a couple ways we can do it. These are 2. So the 10 frames are full and there are 5 of them. 5 10s equals 50. The same goes for the base 10 blocks. If we were to count the individual blocks or the individual counters here, you would count 50. But we don't have to do that because we know that a full 10 frame equals 10. Can you practice skip counting by tens here with me? Let's start with under 50 on the left side. 10, 20, 30, 40, 50. Great job. Can we practice the same thing with the base 10 blocks? Here's 10, 20, 30, 40, 50. So 50 equals 5 tens and 0 ones. But we still have an even larger number to handle next. And that number is 500. How is this number different than 50? Did you say it has another 0? If so, that's the right idea. 500 has 2 zeros. And what does that mean for us? Well, it means that when we model it, we have to use hundreds flats. So each of these blue squares is filled with 100 smaller blue squares. Counting by 100s is a lot like counting by tens. So here on the right side, under 500, we have 100, 200, 300, 400, 500. So 500 then equals 5 hundreds, 0 tens, and 0 ones. I hope that helps you see how those numbers are different, even though they look so similar. So let's recap. Today we learned that numbers are composed of digits with different values. Even though there's a 5 in a number, it doesn't always mean the same thing. We also learned that a 10 is the same as 10 ones. So if you have 10 ones, you have a 10. We also learned that 100 is the same as 10 tens. That's all for this week. Join us next week when we go on our September math walk, where we're going to talk about adding and numbers from 0 to 20. I can't wait to see you then, back out and about in the neighborhoods. Bye! How do you feel about our lesson today? Let's review. We started out talking about 2-digit numbers are made up of tens and ones. As we went through our lesson today, we looked at Fidel and his bags of apples. We organized them into groups in order to count them easier. We talked about 10 frames and how to make a 10. Let's review how to do that. So Fidel bought 27 apples when he went to the store. That number is composed of 2 tens and 7 ones. 20 is made up of 20 ones, but that's only 2 tens. Isn't that confusing? So remember that when we're talking about numbers larger than 1 digit, they're made up of digits with different values. That concludes our time today. Next week, we're going to actually explore a different topic, and we're going to look at ways that you can be a mathematician right inside your own house with things that you might have in your bedroom or your kitchen. And we're going to look at ways that we can make math come alive where you are. See you then!
Hi, I'm Erin Dorsey with Kansas City Public Schools, and I'm here to talk about math problem solving. Last week we read this book, I'm Trying to Love Math, and we talked about how math may not always be fun, but there's a lot of reasons to love it. One in particular is that you can find math everywhere. There is math when you are cooking, when you're listening to music, when you're making music. There's math when you're playing sports like basketball and softball, or when you're playing with your Legos. All of those things involve math in one way or another. But what makes math hard sometimes is solving problems. They're not easy, I'll give you that. But there are some things that we can keep in mind and strategies that we can use that will always help and will make solving those problems really easy. Today, we're going to talk about the 8 mathematical practices. The 8 mathematical practices are the same no matter how old you are. Let's go ahead and take a look at the first one. Make sense of problems and persevere. I'm sure you've heard the word persevere. All that means is to not give up. So in math, when you're problem solving, we want to make sure we can solve problems without giving up. If we give up, we're never going to get to the correct answer. Let's take a look at number 2. Reason abstractly and quantitatively. Abstract and quantitative. Those are big words, but all that simply means is that you can think about numbers in many ways. Math practice 3, model with math. Take a look at that picture. All of those drawings are actually models to solve problems. Now, some of them are really hard problems, and we haven't gotten to those yet. But when we solve problems in math, we always want to show our work, show our thinking on our paper that gets us to our correct answer. And many times we have to find multiple ways to solve that problem. So model with math means that you can show your work in many ways. Math practice number 4, construct an argument and critique others. This can be hard because we never want to make anybody feel bad when they're sharing, but there's a way to do that. It's important that we can explain our thinking and also try to understand others' thinking. And when you don't, what can you do? Ask questions. You ask questions about what they're thinking so that you can understand what their thoughts were when they were solving the problem. Number 5, use appropriate tools. Now, this is really important. Think about being a doctor. Would a doctor use a baseball bat to give you a checkup? No. Would a basketball player use a hockey stick to play basketball? No, because those are not the right tools. Well, in math, you need to use the right tools for the job. So use appropriate tools means that you can use tools to explain why you use them. So for instance, if you need to calculate the perimeter of your backyard, you'd probably use a yardstick. You wouldn't necessarily use a ruler because it would be too small. Math practice 6, attend to precision. This means that you can work carefully and check your work. Mathematicians need to be very precise, so it's important that they keep their work nice and neat and organized so that it's easy to follow. But it's also important that they check it because you may have made a mistake along the way, and that's okay. That's why we have to check our work. Number 7, look for and use structure. The word structure may confuse you a little bit, but all that means is that you can use what you already know to solve what you don't know. And I know that when you are learning about reading and reading strategies, we talk a lot about using what you already know to solve what you don't know. That's called your background knowledge or your schema. And what that is information and experiences that are already in your head. So in math, we like to use that background knowledge, things that we already know, to solve what we don't know. And sometimes what we already know is right there in the problem. Last but not least, look for patterns. Math is full of patterns. And this mathematical practice means that you can solve problems by looking for rules and patterns. Now we're going to take a look at a series of problems and how these 8 mathematical practices can help us solve it. Now we're going to take a look about a problem about huge buildings. Buildings that you probably see downtown or very similar to. They're really, really tall. Have you ever seen buildings when you're walking around that are really, really tall? You have to look all the way up to see them. I have. I've seen them downtown Kansas City, and where I'm from in Chicago, there's lots of really tall buildings. So our problem today is all about those tall buildings. Come on, let's take a look. So those really tall buildings I was talking about, those are called skyscrapers. Here's a picture of a skyscraper. Do you see how high it is? It goes all the way up into the sky. And this particular one is the Empire State Building. This building is in our problem today. Let's take a look at our problem. As we are going through our problem, I want you to be thinking about those mathematical practices we just spoke about and think about how you can use some of those to help you solve this problem. The Empire State Building in New York is 159 meters taller than the Republic Plaza in Denver. The John Hancock Building in Chicago is 122 meters taller than the Republic Plaza. The Empire State Building is 712 miles away from the Hancock Building. The Hancock Building is 920 miles away from the Republic Plaza. Manuel wants to know how tall the Hancock Building is. All right. So we need to find out how tall the Hancock Building is. That's really important. I'm going to go ahead and highlight that because that's what we're going to be trying to figure out. Now, as I think back to our mathematical practices, remember one of the practices is to use the information that we know. So let's figure out, what do we know? Well, we know that the Empire State Building is 159 meters taller than the Republic Plaza. We also know that the Hancock is 122 meters taller than the Republic Building. In the problem here, it doesn't really tell us how tall the Empire State Building is. But there are some other features of this problem that give us that answer. Can anyone see where that information may be located? If you are looking at the picture, you will see the information. The caption says the Empire State Building is 381 meters. That's going to be really important. So here's all the information that we know. And again, what are we trying to figure out? We want to know how tall the Hancock Building is. All right, so let's start working that out. I'm going to use one of the mathematical practices about using what I already know to solve what I don't know. So what I already know is in the problem. I have the Empire State Building, I have the Republic Building, and I have the Hancock Building. Now I also want to attend to precision and make sure that my work is organized so that I can see my thinking, which is why I have 3 different colors here. So going back to the problem, I know I have to solve for the Hancock Building. I want to know how tall the Hancock Building is. The problem states that the Empire State Building in New York is 159 meters taller than the Republic Building. So that means the Empire State Building is equal to 159 more than the Republic Building. The John Hancock Building in Chicago is 122 meters taller than the Republic Building. So the Hancock Building is equal to 122 meters more than the Republic Building. But I don't know how tall the Republic Building is. That is my unknown. So I'm going to use another practice. I need to make a model to figure this out. In order to figure out the height of the Hancock Building, I must know the height of the Republic Building. If I go back to my problem, I also notice that it says the Empire State Building is 381 meters. Right away, I notice I have a total apart and apart. And Greg Tang has taught me that if I have a total in two parts, I can solve any problem. Let's take a look at it as a number bond. This would be an example of a model. If the total height of the Empire State Building is 381 meters, that means my two parts must equal what? 381 meters. I know one of my parts, 159. And my other part is the Republic Building. I don't know that. But I do know that 159 plus this equals 381. How could I figure out this missing piece? I could do a bunch of things. I could add up from 159 to 381. Or, because of fact families, I also know that 381 minus 159 is going to give me this hidden part. I'm going to go ahead and try it that way. So if I take 381 and I subtract 159, I'm going to have to borrow from the tens place. 8 tens, if I borrow 1, it's going to be 7 tens. I put my 10 back down here, and I have 11. 11 minus 9 is 2. 7 tens minus 5 tens is 2 tens, and 3 hundreds minus 100 is 200. So this means that the Republic Building equals 222 meters. Now, I'm one step closer to finding out the Hancock Building. If I know that the Empire State Building was 381 meters, and now I know that the Republic Building is 222 meters, I can easily find out the height of the Hancock Building. So this 381 was equal to 159 and the Republic Building, which we know is now 222. So that means the Hancock Building is going to be 122 plus the Republic Building, which equals 222. So I'm going to go ahead and add that up. 122 plus 222 equals 344 meters. The Hancock Building equals 344 meters. Now I think I'm right, but my mathematical practices have taught me that one of the most important things is checking my work. So I want to make sure that I didn't make any mistakes. The problem tells me that the Hancock Building was 122 meters taller than the Republic Building. If I know the Republic Building is 222 meters, I want to set up a real quick number bond. So if 344 is my total, my problem tells me my parts were 122 plus the Republic building. I figured that my Republic building was equal to 222 meters. So if I am correct, that means that 222 plus 122 equals 344. Is that correct? Yes, that is correct. That wasn't that bad. My mathematical practices really helped me solve that problem. So let's recap. I think I may have used almost all of those practices to solve that problem. The first thing I had to do was to make sure that I didn't give up, because that was a lot to do, but I didn't give up. So I definitely used the first practice. Then I also used the second practice because I had to think about numbers in so many ways. I thought about numbers as addition and subtraction. I thought about them in number bonds and bar diagrams. So I had to think about numbers in a variety of different ways, and that really helped me solve the problem. I also had to show my work. The only way for me to have solved this problem was to make sure that all of my work was written out so that I could stay organized. And with that, I absolutely had to make sure I was precise. I didn't really critique the reasoning of others, but I definitely had to think about my own reasoning. And then I used lots of models. The models, the number bond and the bar diagram, those really helped me solve the problem. They helped me to think about numbers in a very basic way. I know that all problems can be solved by thinking of them as a total and some parts. And I hope that once you realize that when we were working our problem out today, that you realize how easy it really could be. When you come across a word problem, one of the best things you can do is think about the parts that you already have, and that will help you figure out the unknown. As you can see, we always use our 8 mathematical practices. You may not use them all, but you definitely use them as you are thinking and working out math problems. These practices always help you out in life too, because it's important that we always persevere and we don't give up. It's important that we use correct tools. It's also important that we listen to others and we ask questions. I really hope you enjoyed yourself, and I hope that you are able to look at this problem and see that you really do love math. See you next time.
Good morning. Hello, my name is Mrs. Fender, and this is Math for Middle School. Today we're going to learn about how to find the amount of discount and then take that and figure out how much an actual object or something that we purchase will cost. So, give you a few minutes to get some things together. You'll need paper, pencil, calculator if you have handy, and a great attitude. And I'm going to give you a couple seconds to get ready to learn and see it in a minute. Okay, so the object of today is going to be determining the cost of how to apply a discount and find the ending cost. And we're going to talk about our simulation that we've been doing for the last couple weeks, and we're going to talk about paint. And I've got 2 kinds of paint for us, and they're going to be pretty generic, paint 1, paint 2. Paint 1 is going to cost $43. Paint 2 is going to cost $30. They're both going to be at a 20% off discount. So normally we're going to ask for two things. Number one, what is the discount? And number two, what is the actual cost after the discount is applied? What are you going to pay at the register? So the lesson objective is to find the cost of a purchase after a discount is applied. We're going to continue our simulation with our interior design, and I'm going to use two kinds of paints today. The first kind is $43. The second kind is going to be $30. Both are going to have a 20% off. So we're going to figure out the cost and we're going to figure out the discount. Now there's a couple of different strategies we can do with this. And the first strategy we're going to do is a pictorial. I'm going to show you what it looks like as a picture. We're going to determine the discount and the cost after applying the discount. We're going to talk about it in two ways. The first way is going to be pictorial. The second way is going to be abstract. Now, when we talk about pictorial, we're going to be using a tape diagram. A tape diagram is basically a large rectangle that we're going to break into pieces to represent our parts. So let's draw the tape diagram. So this represents our whole. So this is going to be 0%. This is going to be 100%. Now our whole, which is our total cost, is going to be $43. Now a couple of things you need to think about. How many times will 20 go into 100? There are going to be 5 groups of 20 in our bar model. So we're going to divide this into 5 sections. So this would represent the 20% mark. This would be 40%. This would be 60%. This would be 80%. Now our whole is going to be $43. Because we have 5 sections of 20%, we're going to divide 43 by 5. So I'm going to say 43 divided by 5. That's going to go 8 times. That's 40. Add my decimal, carry my placeholder. So that's going to be 8.6. Now remember, we're using this to find our discount. So it's going to be 8.6, which really is $8.60. So each of the 20% sections is $8.60. Now, because we have a discount, we need to take off 20%. So that means we get to subtract from our total price $8.60. So we're going to come over here and do 43 minus 860. Go ahead and add my decimals. I'm going to have to borrow. I think some people say shift now. So that's going to be 0 for shift or borrow again. So that means that our final price, this is our discount, this is our final price or cost. If you didn't want to subtract, is you have $8.60 times 4 remaining sections. If you would multiply that together, that would give you $34.40 as your final cost. That's the same thing as we just got previously by subtracting. Now let's take a look at our abstract. We're going to use the same amount. This time we need to change that percent into a decimal. And when we think about that, we can say 20% is a fraction in itself. It's 20 over 100. And when I say 20 hundredths, that automatically tells me what it's going to look like as a decimal. if I can remember my place value chart. So that's going to be 0.20 for any of your calculations, because anything times 0 is 0. So that's going to be 0.2. So I'm going to take my initial cost, my original cost, and I'm going to multiply it by my percent discount. Oh, let's spell that correctly. And that is going to give me my amount of my discount. So my original cost is $43. I'm going to say, okay, my discount, my percent discount as a decimal is 0.2. And what is that going to give me? So when I multiply those two things together, that's going to give me my $8.60, or 8.6. Remember, this is my discount. Now to find my purchase price, you're going to say 43 minus $8.60. That's going to be $34.40. That's going to be my final cost. Now, there's a strategy number 2. Instead of figuring out the percent discount, you figure out how much you have to pay after the discount. So if I know my whole is 100, I have to pay 100%. And then I'm going to take away 20%. That leaves me with 80% to pay. Instead of coming up and multiplying times 0.2, I'm going to change that 80% into 0.80 or 0.8. So again, I'm going to do 43 times 0.8 equals $34.40. This is my final cost. So 2 different ways to look at it. Do I want my discount, or do I want to multiply times what I actually have to pay? There's a third strategy. It's also with abstract. It's using ratios, and I want to show you that very quickly. And ratios is basically 2 fractions. So I have my discount, and as my denominator, I'm going to put my original cost. That is going to be equal to my whole, and this is going to be my percent of my discount. So when we substitute, okay, I don't know the amount of my discount, so I'm going to leave that as variable D. I do know my initial, or my original cost, is 43. I am going to write, and this is going to be my percent discount as a fraction. And I know 20% as a fraction is 20 over 100. Now I'm going to have to do some multiplication. So I'm going to have to figure out, okay, what times 100 is going to give me $43? I'm going to multiply that times 0.43. Anything that you do to the denominator, you have to do to the numerator. So I'm going to do the same thing up top. And I'm just going to do my work off to the side. I'm going to say 20 times 43 hundredths. And once I multiply that, that's going to give me my 8.6, or 8 6/10. I'm going to change that to my money, and that's going to be $8.60. That is going to be my discount. To figure out my final cost, I can just say, okay, $43 minus $8.60. That's going to give me my $34.40 as my final cost. So we've talked about 3 strategies to figuring out discount and the final cost. We can use a tape diagram, which is pictorial. We have 2 types of abstract. We can either use our decimal algorithm or we can use ratios. So to practice, I have one that I would like for you to do on your own. It's again with paint. We're going to keep with our theme. This time its purchase price is originally $30. The discount price is 20% off. Your turn, using any of the strategies you've just done with me, find the discount and find your cost after you apply your discount. That's all we have for today, and I hope you have some things that you can do at home to practice this. In conclusion, that's our lesson for today, and I hope you've enjoyed it. This week, we'll continue with this next week. It's been my pleasure having you in class. My name is Mrs. Fender, and I'll see you next week.
Hello, my name is Marcelina Lirius.
Hello,
and
my name
this
is Marcelina
Math Monday.
Lirius, and this is
Today
Math
we're going
Monday.
to solve one
Today we're
variable
going to
equations.
solve one variable
You will need
equations.
a pen and a paper.
You will need a pen
And if
and a
you're
piece
ready,
of
let's
paper.
get started.
And if you're ready,
After this
let's
lesson,
get
you should be
started.
able to solve
after
one-step
this
and
lesson, you should
two-step
be able to
equations.
solve one-step
You should
and
also be
two-step
able to
equations.
explain or justify
You should also
each
be
step
able
in
to
solving
explain or
equations.
justify each step in solving
So
equations.
what does it mean to solve an equation?
So what does it
Let's
mean
find
to solve an
answer to this
equation?
question as we go
Let's
over
find
the
answer to
problems
this
in
question.
this lesson.
And first, let's
We'll
review
recall
some
of the
vocabulary words or properties of
that you
operations
have
and
learned in middle school.
equality that will help us solve
So the properties of
equations.
operations. In this
So the
lesson,
properties
we will
of
focus on
operations.
two properties.
In this lesson, we will
The
focus on
inverse
two properties, the
property
inverse and
for
identity
addition
properties.
and multiplication.
The inverse property for addition states
And
that
the identity
a number
property.
plus its inverse gives
So
us
for
0.
inverse property for addition,
And for multiplication, a number times its multiplicative
plus
inverse is
its
equal to 1.
inverse is equal to 0.
Then the identity property for
And for
addition states that
multiplication,
a number plus 0
times
is still
its
the same
multiplicative
number.
inverse gives us 1.
And for multiplication, a number
Identity
times 1
property
is
states
still
that
the same number.
For addition,
So we call
a
0
number
as the
plus
additive
0 is
identity
still the same number.
and 1 as the
And
multiplicative
for
identity.
multiplication, a number
We also know
times
that
1
addition and
is still the
subtraction
same
are
number.
inverse operations.
We call 0
Multiplication
as the additive
and division
identity
are also
and 1
inverse
as the
operations.
multiplicative identity.
We will use the properties of equality in
So we also
justifying
know
each
that
step in solving equations.
Addition and subtraction
By
are
properties of
inverse
equality, this
operations.
simply means that if
So
we have
with
two quantities that
multiplication
are
and
equal,
division. We will also
okay,
use the
whatever
properties of
operation
equality.
is performed on the left
So
side
what
of
these
the
properties
equation,
actually mean,
that same operation must be done
if
on
you
the right
have
side to maintain the
two
equality.
quantities that are equal.
So we have the addition
Whatever
property of
operation is
equality,
performed on the
subtraction
left
property of
side
equality,
should
multiplication
also be
property of
performed
equality,
on
and
the
division
right side.
property of equality.
Now
I will
I'm going
model
to
to you how to solve
one-step
one-step
equations.
So when we say solve,
So
this simply
when
means
we
we're
are asked to solve an
finding
equation,
the value of the
we're
variable,
actually finding
whether
the
it's
value
x,
of
y,
the
or
variable
z,
x that will make
the variable
equation
x
or
here
this statement true.
that will make this
So let's start
equation
finding the solution by
so let's
using
start
inverse
first
operations.
by using inverse operations.
So if we have
So if we
x
have
plus 7
I mean
equals 12,
if we have x
we need to isolate
plus
the variable.
7 is
That
equal
means
to
to
12.
keep the variable on one side.
We need to keep the variable
So
or
we will
isolate the variable on one
7
side. So by
finding
using
the
inverse operations, we
of
will
adding 7,
eliminate 7. So we have
which
x
is
plus 7 minus
subtracting
7,
by 7.
12 minus 7.
And if we
So we
subtract
subtract
7
both
on the left
sides.
side, we will also
We subtract
need to
7 from both sides
7
of the
on
equation.
The right side.
And this is justified
And
by the
this is
subtraction
justified
property of
by
equality.
the
Then we know that a
subtraction
number plus
property
its
of
inverse is
equality.
equal to 0.
Then
So x
we now
plus
have,
0 is equal to
so
5. Again, this is
let's recall,
justified
7
by
minus
the
7
inverse
is
property
also the same as 7 plus its
for multiplication.
inverse. And this will
And
give us
also,
0.
by identity property,
which
we
means
know
that
that
this
a number
step
plus
here,
0 is still the number.
x,
So x plus 0
this
is equal
part
to
here
x
is
by
0.
identity property. So x
And
here will
we
be
now
equal
have
to 5,
5.
and this is
So
justified
this is
by the
justified
identity
by the
property.
inverse property
So we call
for
x
addition.
equals 5
Okay?
as the
By
solution
inverse
to the
property.
equation. Now I will show you how to solve equation using the bar
Then,
model. So if we have x plus 7 equals
let's look
12,
at the
these
next
two
step.
quantities are equal,
If
so
we
we
have
represent
a
each
number
side of the
plus
equation
0,
by the same bar. So x plus 7, and
this
here it
gives
will be
us
12.
still the
Then
same
we're going
number
to
x,
decompose
and
x
this
plus
is
7
justified
into x
by
and
the
7,
identity property.
and also 12 as 7 in 5.
So we call x equals
So
5
these two are
as the
equal, so
solution
then x must also be
to
equal
the
to
equation.
5.
So which
So
means that
this
if we substitute x with
is what we
5, this
call
will become
the
a true
solution.
statement.
Okay, we arrive at the same
Now I
solution.
will model to you how
X
to
is
solve
equal
this
to
equation
5.
using the
So it's always
bar
important
model.
to check our work.
So if we have the
x is
equation
equal to
x plus
5,
7 equals
will this
12,
satisfy the equation?
we
5
represent
plus 12 is equal,
the
5
left
plus
side of
7
the
is equal
equation
to 12.
by
So
1 bar, which is x
12
plus 7,
is equal to 12.
or
And
the
this
same
is a
rectangle.
true statement.
So now we're ready to solve two-step equations. We're going to extend our knowledge in solving one-step equations to solving two-step equations. So let's solve the first example. 4x plus 1 is equal to 13. Let's start using inverse operations. So if we have 4x plus 1 is equal to 13, our goal is to keep or to isolate the variable on one side by eliminating the other terms. In this case, we need to get rid or to eliminate 1 from the left side. Using inverse operations, we will now have 4x plus 1 minus 1 equals 13 minus 1. And this is justified by subtraction property of equality. And we also know that a number plus its additive inverse is equal to 0 by inverse property. So we now have 4x plus 0 is equal to 12. And this is justified by the inverse property for addition. Then, by identity property, we know that 4x plus 0 is 4x is equal to 12. And this is justified by identity property. Notice that the two-step equation is now reduced to a one-step equation. So we will continue using inverse operations. So the inverse of multiplying by 4 is dividing by 4. And this gives us, okay, 4 divided by 4 means 4 times its multiplicative inverse, and this will give us 1. So we will now have 1 times x is equal to 3. So this is justified by the inverse property for multiplication. By the way, the first one here is justified by the division property of equality when we divided both sides by 4. So 1 times x, again by identity property, gives us x equals 3, and this is justified by the identity property. Now, using the bar model, we represent the left side of the equation by 4x plus 1, and the right side of the equation will be represented by another bar. They are equal, so that means we have two equal rectangles here. Then we can break down 4x plus 1 into 4x and 1, and 13 can be decomposed as 1 and 12. Okay, then further we can break down or decompose our 4x as x, 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 and x. Then copy the 1, and we're going to decompose or break down 12 into 3, 3, 3, and 3, and 1. So notice that these are equal. So x is equal to 3, x is equal to 3. So our solution here is x is equal to 3. Same as what we arrived using the inverse operations. To check our answer, let's substitute. Our x is equal to 3, so 4 times 3 plus 1 is equal to 13. So 13 equals 13 is a true statement.